to be playing the role of interviewer, and you'll be the interviewee. So we're going to give you a taste of, like real interview, but this is a prep for your mock interview, which is a prep for your real interview. All right, so see how many stages you go through to prepare. But hopefully you've gone through the material that we've learned last week. The questions should be, from the stuff that you learned last week and today. But more importantly, if you haven't already, I've posted a guideline there in the prep. So make sure you look through that, because that's what we'll be looking at, right? Are you communicating? Are you basically thinking out loud, talking through your thought process? Are you asking questions, clarifying assumptions? And then, so coding is important, but don't jump into code to begin with without clarifying assumptions and such, right? Because what the interviewer is looking for is, if we give you a task, are you going to ask your team members to make sure you're on the right path? Or are you just going to go off on your own and, try to solve the problem, and maybe you're approaching the wrong direction? So we want to make sure. So that's what really interviewers are looking for a lot of the time. So we want to make sure we prepare you for that. If for any reason, so if you don't have a mentor session today, if it's tomorrow, then your interview will be tomorrow. So just so you know that. But if for any reason your mentor forgot, or for some reason you're not having the interview, please let them know, remind them. Or just let me know, ping me anytime. Let me know that you're supposed to have an interview today, but you didn't, so then I can follow up, okay? But every one of you should have part of your mentor session should be spent going through the interview. And then, of course, they're going to fill out a form, send it to me, and then I'll forward that to you guys as a feedback. Okay? All right. What other? I think that's all the announcements I had today. So let's get started with hash maps. You guys can see my screen okay? All right. Let's go here. All right, so today we're talking about another data structure called hash map. So arrays and linked lists, the ones we learned last week, are known as sort of linear data structure, right? So arrays can be accessed by index, linked lists can be traversed through, and we can find the item in the pool of data set that we have. So there's this notion of, you start at the beginning, which for arrays starts at index 0, for linked list starts at the head, right? And we basically traverse through the data and then find the data. So those are known as linear data structures. Start somewhere and then end at the end, and in between, one by one, to find. Hash maps are. So hash maps have what's called key value. So the idea of index or the end position, right, is not so important. Bring the data, and therefore we're finding the data is by what's called association, right? And that association is done by what's known as key value pairs, right? So for each data that we're going to store, so each data is going to have, two part is the other part is if I want to store Tohida, right? Instead of just storing Tohida, I'm going to give a number. It could be a customer ID. It could be like a word called first name or name. How do you want this? Did someone have? No, wait. What's going on?
We're having connectivity issues. It sort of cuts in and out.
Okay, you guys can't hear me? Okay. Let me reload. Okay, so just give me a second. Let me reload. I'll be right back. Either with index 0 or at the head, and then iterate through each item in the data set to find it, right, or to store it. But for HashMap, we do this by association, right? So for example, key value pairs, right? So if I want to store Towhida, right, not only I would have the value, which is Towhida, I would have a key associated with it. And this key could be a first name, key could be name, key could be a customer ID or just a number, right? So we know that if we say, okay, customer ID 1 is associated with the value Towhida, right? Customer ID 2 is associated with the value someone else. So that's how data is stored in hash maps. So hash maps are also known as associative array, or in Python, they're called dictionaries. So the whole idea here is storing data using key value pairs. Okay, so therefore, if we are looking for the data, we would be looking by the key, and when we found the key, the value that's associated with it. I still can hear me and see me okay, right? Just making sure. No. Okay. So you can hear me but not see me? Which one? Chops in and out. Okay. Okay, how about turning off camera? All right, so I turned the camera off. Can you guys see the slide? I restarted my computer. Okay, you guys can see the slide. Can you hear me okay now? Camera. All right, I'll just keep the camera and all right. Uh-oh, thumbs down again. That's not good. All right, guys, let's try this one more time. All right. Is there? Can you guys hear me? Can you guys see this? Wow. Can't hear anything now. That's not good. Modem, router, computer. So let's see what happens. And again, if it starts fading, let me know. I don't think it's my network, but I'll figure that out later on. Okay, so moving on to HashMap. As I said, these are associative. So hash map is an associative data structure. So for every data that you store, you're going to have a key associated with the data. And then when you try to find the data, right, you're going to have to do this using that key. Okay, so let's just do a demo. So for an array, right, suppose this is an array right here, right? And here, so this is a fixed size, and I'm trying to store data. And suppose I have a bunch of data here, and I start at index 0, and then I go through each index, and in each memory slot, I basically store the data, right? So for a linked list, again, I start at the head, and then using my next pointer, I store the next item on the next slot, and then the next item on the next slot, okay? So let's see how hash maps are different, okay? So before talking about how hash maps are different, think about how the data structure looks like, okay? So let's talk about how it looks like. So let's take this array into consideration, okay? So in the traditional sense, right, if I want to store something in this array, I would start at index 0, right? And let's say I want to store T here. And I would go to index 1, I would store A here. I would go to index 2, store U here, right? So now let's change this data. And for each one of these, I'm going to have a key associated with it, right? So let's say I could have, I'm just going to come up with numbers here, right? So let's say I have 3T, and then 4, right, A, and then 5, or let's say 6U, right? So notice that these are key value, okay? So T is the value, and the key for T is 3, right? So 3 is identifying that data, right? So anytime, instead of looking for T, I'm going to looking for the key, which is 3, right? So forget about these now, right? So here, because this data is a key value pair, that's the association. When I store that data in my data structure, right, I'm going to use the same structure. So I'm going to say, okay, let me take 3 and find basically a slot for the key. So let's say 3, right? So it's 0, 1, 2, 3. So I can pick this one here, right? And store T there, right? And 4, so 0, 1, 2, 3, 4, right? So this is 4, and I can store A in there. So basically, I'm using the key to find the location, right? And I'm storing the data at that location. That's the difference between hash map and a regular array or a linked list. Okay, so we do use arrays as the underlying data structure, and we use linked list as well as the underlying data structure to create hash maps. But notice that the use of the array is not the same as traditional arrays, right? In this case, notice the one thing that we couldn't do with arrays is the gaps in memory, right? But here we can. I don't have anything here. I don't have anything here. I don't have anything here. But in slot 3, which is the key for T, I have data, right? Because I am not traversing the data structure from beginning to end. I am looking at it based on the key and finding the value that belongs to that key. Okay, so that's why hash maps are different. That's why they're associative data structure, okay, rather than linear data structure. Now, let's see how we're doing. Okay, we're doing good so far, right? You guys can hear me and see. Okay, wonderful. Good. So in order to have this structure here, right, there are a couple of things that we need to consider. in order to create hash maps. One thing is called hash functions, right, or hashing. So you guys are probably familiar with this term hashing from your authentication material that you learned before, from encrypting and decrypting passwords and username that you did in the past, probably in Node. Also, you've probably heard hashing and hash function with cryptocurrencies and blockchain and such. So hashing is basically the core of those technology, because hashing is what basically masks the underlying data. So the concept, we use that concept of hashing, but in a different way when we come up with the hash map data structure, right? So we create what's called a hash function. And the sole purpose of the hash function is to take this key, right, that the data is associated with, right, take the key and find a proper place for it to be stored. So if I'm using an array as the underlying data structure to as a hash map, my hash function is going to take the key of my data and it's going to find me a slot in that array. And it's going to say, this key should go to this location, right? This key should go to this location. That means the data that's associated with that key is going to be stored in that location. That is the sole purpose of a hash function. So then how do we, what goes inside a hash function, right? So how do we implement a hash function? There's actually a certain way to implement it. And we follow certain characters of a hash function. So number one property of a hash function is that the data that you're sending can be of any size, right? Think about a password, right? Your password could be 8 characters long. Mine could be 16. Somebody else's could be, 25, 30 characters long, right? And others can be 3. So these are different size data, right? But so as an input to the hash function, you can give it any size data. The function is always going to return a fixed size data. So that's number one property. And usually that fixed size data is 32-bit integer, right? Because that works for most machines, right? But it could be anything else. But for our purpose, we're going to say, okay, we're going to make sure that you can send any size data to the hash function. It's always going to return a fixed size data. Okay, now these properties are important for you guys to know if you are actually writing your own hash functions. In most cases, you probably don't. You're not going to, right? Unless you're going to get a job, as a blockchain developer, then you're going to learn more about hash function and write your hash functions. But for our purpose, we are giving you a hash functions. But I want you guys to know what's in it, right? What's the magic that's happening. So that's what the purpose of this slide is strictly learning purpose, okay? So given a arbitrary size data, you always get a fixed size data. So that's number one. Number two is the same input will always give you the same output. So imagine that if you are typing in a password, right, and that password is hashed and placed in a database, using basically the hash string is stored in a database for security purpose, right? So every time you log into the application, right, and you type in your password, although the password is being hashed and stored in the database, it has to somehow decrypt that, right, and give you that output. So if every time it hashes it and gives you a different output, you're not going to be able to log into the system, right? So the same input, if my password is hello, right, if you're hashing that same input should always give you the same output. okay? And the third property of a hash function is that our goal is always to create what's called perfect hash function, right? And what is a perfect hash function? A perfect hash function gives you equal distribution of output. And this third property is very much useful for our purpose, for our hash maps, right? Hash functions that are going to be used to create hash maps. So what does that mean by equal distribution? So if I have a hash function here, right? Suppose I have a hash function and I'm sending input to this hash function. And what does it do? The hash function gives me a slot in this array, right? So if this hash function is written in a very skewed way, right? Suppose every single output that's coming out of it's towards the end of this array, right? It's giving me, let's say, 4, 5, 6, 7, and so forth, rather than the 0, 1, 2. That's a skewed hash function, right? So we want to create this hash function in such a way that every time we send an input, right, the output should be evenly distributed, right? So the first slot can be 6, the second slot should be 0, the third slot could be 4, and then the fourth slot could be 1. So we want these locations should be to be sort of equally distributed, right? So equal distribution of output given whatever input you're giving the function, right? Which is actually not easy to do, right? So you have to put a lot of thoughts into creating the hash function. So these are some of the properties of a good hash functions that you need to basically create hash map. So let's talk about some very, very simple hash functions, right? As this example showed you, right? If I have a key that's numeric, my life is easy, right? I have an array here as my underlying data structure. I'm using that as a hash map, and I say, okay, my key is 3, go to the third slot and put this value in there. If it's 4, and then go to the next one and put the value in there. So numbers always makes our life easy. So a very, very simple, right, hash function for if you have a number as a key is basically take the number, right, mod it with the hash table length. So if my hash table 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, right, 8, 9, 10. I'm just going to make our life easy. So my hash table length, right, is 10. So what this means that I only have 10 slots. That's how big my hash table is. And I'm going to store data in that size table, okay? So then now let's go back to my data. My data is T and its key is 3, right? So if I want to store T in this hash map, right? What I'm going to do, according to my hash function, I'm going to take my key and mod it with my hash table size, and that will give me the slot where I can insert T. So I will send this to my hash function. My hash function is going to say, okay, 3 mod 10, right, is 3. So 0, 1, 2, 3, that's where T goes, right? If I have 10, and let's say 10 is my key, and let's say I want to insert JS, right? So then I'm going to say, okay, 10 mod 10 gives me 0, right? So JS is going to be stored in index 0. Okay? So questions on this, guys. How this hash function is done. The purpose of this hash function is to find a slot for my key so I can store the data. And this is the simplest hash function you will ever see. Questions so far? Okay. Everybody good? Okay. You guys can still hear me and see the slides? All right, good. All right, so as I said, that our life is really easy if we have keys that are numeric, which is actually not realistic, okay? So in most cases, our keys are actually either alphanumeric or, alphabets, right? So in that case, how do we store that data in a hash map, right? So imagine, let's take this example. Imagine that I have data where I'm saying, okay, David is, what is David? David is vocal? Yeah, David is vocals. Okay. I could also say Tohida, right, is guitar. Okay. So we could have data that looks like this. So this is the key, and these are the value, right? So you're going to say the key is Tohida and the value is guitar, right? You're associating the value guitar with the key Tohida. You're associating the value vocals with the key David, right? So your data can also be stored in this way. So this is key value. So notice now the key is no longer numeric, right? It's actually string. So then how do I want to store this data, right, in this hash map, in this slot. Okay. So if we want to do this, then what do? We need to, because this index, these are numeric, and this is a string. So what we're going to do is convert our string to numbers, right? And then find a slot here and store the data. Okay. So in that case, it's thankfully JavaScript has a built-in function which converts, letters to numbers, and it does so by using the ASCII the ASCII value of the string. So if you guys are not familiar with the ASCII code, right, you can definitely look at this chart. Notice here, so you have different number system here. Here's binary, here's decimal. Also, you have, where's my ABCD? Here. So notice that capital A, right, is 65, and small a is 97. So I want, my key is David, right? So I would go, here is David. D is 100 plus A is 97, right? V is 118. And then I is 105, right? So basically what I'm doing is I'm picking the numeric value of each character. Notice I'm going through a for loop, extracting each character of this key, David, and taking the numeric value of that and adding them together, right? So my total is going to be the numeric value of DAVID added together, right? So it's going to give me a big number, right? And I'm going to mod that with my hash table length, right? However big my table is, this could be of length of size 10, of size 20, of size 10,000, whatever the size is, right? I'm going to try to map that key, right, to a slot in my hash table, right? So let's imagine David gives me, I think I have the answer here somewhere, not here. Let's imagine David gives me, I don't know, like 500, right? So imagine David gives me 500, right? And my hash table length is 10, right? So I'm going to mod this, and then this should give me 0, right? And so therefore, David is going to go to this first slot right here. Okay? So then here in the first slot, I'm going to store my key and then the value associated with it, vocals. Okay? Suppose Tohida gives me, I don't know, like 699, right? And then I'm going to mod that with 10, right, to find a slot that belongs to Tohida, and then I will put Tohida and guitar in that slot. Suppose something else gives me, I don't know, like 31, right? I'm going to mod 31 by 10, which is going to give me 1 right here. Okay. So again, this is the simplest hash function that you can ever find. Okay. Take all the keys, convert them to numbers, take that number, mod it to your hash table size, and then find the slot in that table and insert the value there. Okay. Question on this, guys? So far, so good? Okay. All right. As I said, that notice that if you compare these two hash functions, right, to this, it actually does not follow any of this. Probably the second one is met, but these are not all the characteristics are met. Okay, so this is not a very good hash function. We're going to run into problems with this, right? So we want to make this hash function better. So this is a much better hash function, which actually follows all three of these properties. Okay. All right. I know that there are some scary symbols here, like, my God, what is this? What is this? What is this? Right. I'm going to explain each line of this to you guys so you know that it actually makes sense and it's not something that's arbitrarily put in here. But I will also tell you that just know this for information purpose, right? There's been lots and lots of research on good hash functions. There are actually very, very good hash functions around. So you will probably not reinvent the wheel and come up with your own. You'll probably use one of these. And by the way, this code is written here based on good hash functions. Like, there are many research that says if you use a large prime number, and by the way, they also tell you the 31 and 37, these are good prime numbers to use for writing hash functions. People have done research on these, so we basically use them to implement it. Okay, so again, know what's going on here, but you don't have to worry too much about how, what's happening underneath this logical and, right? What's happening underneath this bit shift right? So you don't have to worry about that too much, right? Just know that what that line of code is doing, just so that you understand that this hash function is meeting the properties of a good hash function. So some of these you should be familiar with. It looks just like this, right? I'm taking a key, a string, taking each character of that string, converting that to number, totaling the number, and then modding that, right? So here, let's see, you can actually see some similarities. I have a string, let's say David, right? I am taking each character from David, converting that to my numeric value, right? And I'm also adding them. Now, what are these, right? So first, I have just a variable called hash. And I initialize that variable to a large number. And this is actually, excuse me, this is actually a very large prime number, right? That's all. So I'm basically taking a variable called hash, and I am initializing that to a large prime number. Okay. Then I go through my key, David, and I extract each character of David and convert it to its numeric value. But I don't stop there, right? In my previous function, that's all I did. But here, I actually go and do a little bit more. So here, I'm adding that to my variable hash, okay? But before I do that, I'm gonna make my variable hash even more better, okay? By basically shift it left 5 slots. So why am I doing that? So what is hash? Hash is 5381. And when you shift it 5 slot left, it becomes a different number. It becomes actually a very large number. So let's think about this for a second. Imagine, and the way this is done is, so for example, hash. I'm going to use a really small number for our purpose. Let's say hash is 5, right? So remember, I talked about binary the other day. So what is binary version of 5? That's 101, right? So that's 5 in binary. Now, if I do hash, right, shift left 5 slot. So what am I doing is I'm saying, okay, so 1, 2, 3, 4. So it's 1, 2, 3, 4. So 101 was here, 101, and I shifted it 5 space, right? Notice this is no longer 5, right? It's 2 to the 0, 1, 2, 3. So it's 2 to the 4 plus 2 to the 6. So that's 32 plus 128, right? So 128 plus 32. So whatever this number is, I just converted hash, which was 5, to a really large number by shifting it 5 slot left, right? And that's exactly what's happening here. I take my 5381, right, and I bit shift it 5 slot to the left, making that a really large number. So is this always done? No, you can actually achieve the same thing because our goal is to make this number a really large number, right? Because we want we want a perfect hash function, okay? So I can actually do this by multiplying hash by 31, which is a prime number, or 37, which is another prime number. You would still achieve. So imagine 5381 multiplied by 37 is a large number, right? So that can be done. Or you could do it at basically binary level, which would be faster, right? Because if you are multiplying 5381 with 37, both of those numbers will be converted to binary and then do binary multiplication, right? So instead of that, you can achieve this as a little bit faster. Okay, so bottom line, very large number, right? Plus 5381, large number, plus each character in the key. Add them all together, right? You have a really large number. Okay? All right, so that's what this line is telling you, giving you a really large number. This second line, okay, what is that second line for? So notice one of our property says that doesn't matter what size data you enter. So you can enter David, you can enter Tauhida, you can enter, I'm the best person in the world as a key. You can enter a really large or a really small size data. You want to make sure that you're always coming back with the fixed size data, right? Because each of these memory blocks has a certain size, right? And for different architecture, 32-bit model architecture is going to be different than other architecture, right? So you want to make sure that whatever size data you send, right, the blocks that you're allocating will be, the data that comes back is not larger than the block size you have, right? So we always want a fixed size data to come back to us. So this line gives us a very large number, which has the danger of being so large that we can't, like, basically we can't accommodate that, right? So we use this here to make sure this logical AND converts, ensures that the data you have, right, when you logically AND it with itself, it ensures that it's a 32-bit integer. Right? And that's all we're trying to do here. Okay? So very large number, making sure it always gives you a fixed size number, right? And the last one here, so by doing these two, we also run into a danger of the number system, which goes from negative to positive, right? So I can have, notice that I can have a number that goes from negative something to positive something. Now, these index in my arrays are always going to be positive. So if I end up with a data, if I end up with this hash that's giving me an a signed integer, right, which can be negative, I have a problem, right? Because a very large negative number mod with the table size is going to give me a negative number, and I will have a problem. So I want to ensure that this is always a non-negative number, which means we will only consider 0 to the positive part of it. Okay, so this is ensuring that this number, this very large number that we just got, right, is always going to be a positive number by basically bit shifting it to the right and making sure that there is a 0 in there, right? So in binary, if you have a 1, if you have reached the maximum fixed size and the last one is a 1, that indicates in binary it's a negative number. So we want to make sure that that number is 0, right? Making sure that it's a positive number. After all of this, right, David gives you this. So notice if you just take David and run it through ASCII, right, you would probably not get this number. You'd probably get something like 500 or less. But by sending it through this hash function, right, ensuring that it's a 32-bit and making sure it's a positive number, I get this gigantic number. Okay, that's what David is, this. And now I'm going to mod it with my table size. And then find out that when I mod that with my table size, I get a 3. And now 3 is within my table size because that's what I modded with. And so David is going to go to slot 3. Okay. Okay, again, if it's really hurting your brain to see all of this, I want you to, if you understood it, great, wonderful. But if you're having difficulty, at a minimum, I want to make sure that you understand the fact that this is a good hash function that follows the properties to create a good hash function. And all this function is doing is taking a key and giving you a numeric value that you can map to your hash table, which is fixed size. Okay, so now David and vocals is stored here. Okay, any question on this, guys? How are we doing so far? Okay, so if you have ever used Python, right, and you've used dictionaries, that's what hash maps are. But underneath it, all this is happening underlying it, underneath it. They have used objects, right? That's objects are key value pairs. This is what's happening. This is how objects are stored, right? Okay, so all right, let's move on to the next topic in hash maps. Hash maps are wonderful data structures because they give us O1 access, O1 insertion, O1 deletion, which are constant, right? The best big O you can ever find. So notice that I want to store David here, right? I'm not iterating through my long list of data. I'm not trying to find an empty slot. I'm not trying to find the memory block and playing with the next pointer, nothing like that, right? I take my key, I do the calculation, which is O of 1, right? All arithmetic calculation in a program is basically constant, right? Yes, I have to go through if you have a long string, you do have to go through that, but that's separate than the hash map itself, right? So if you have this large number and you want to find the slot in this data structure, that's O of 1 because you go straight to that slot and insert it. Okay, so wonderful data structure, which has an enemy, which is called collision. So notice here, right, if I wanted to insert David, right, David is giving me slot 3. So I go to slot 3 and I insert David and vocal. Great. So now I have a different key. Notice that the key is not the same, right? The key is Greg. So I send Greg through my really good hash function that I came up with the hope that I would have equal distribution. And in most cases, I will. But even then, even the best hash function will have this problem, which is called collision, right? So Greg, when I send Greg through my hash function, I get this big number. And because my hash table is fixed size, and in this case, it's a really small one, Greg is giving me a slot 3 as well. So it's telling me, by the way, you need to insert Greg in slot 3. So then I go to slot 3 and I see that David is already there. And I can't delete David. That's part of my data set. So that's called collision. Different keys fighting for the same slot. That's collision. Collisions are enemies of hash table. Therefore, we've taken, we have strategies to actually deal with collisions. There are 2 ways to deal with that. One is an easy one called open addressing, right? So if I assign you a particular seat, let's say, right, and you go and you find that seat is taken, somebody just came in and didn't care and just basically sat on that seat, right? So you're a nice person and you say, oh, okay, so you've taken my seat, but the seat next to yours is open, so I'll go and sit there. Right? That's called open addressing. Take the next open slot after your seat. So here, 3 is occupied by David. So Greg says, okay, is 4 taken? 4 is open, so plunk yourself in 4. And if 4 was taken, Greg would go to 5. If 5 was taken and I'm at the end of my array, go to the beginning, right? And find an empty slot. And if there's no other empty slot, we go to array resize, right? We go and find a new location, right? So this is open addressing, right? Basically find the next available slot. So a lot of people says, well, I don't understand. Why can we not? So why do we have to go to 4? Why can we not go straight to the beginning to 0 and find that? You can't do that because insertion, right? The way you insert something in the data, in the data structure is exactly the way you find something, right? So imagine if I want to find Greg and I go to, because Greg is going to give me 3, and I'll go straight to 3, and I see, and I'm going to compare. And what's in 3 is not Greg, it's David. That means I know I have collision. So then what do? Do I just go to the beginning and start scanning everything? That's not how it's going to work, right? So then I will move to the next slot to find Greg, and the next slot to find Greg until I reach the end. Then I'm going to go to the beginning, right? So I can't just straight go to the beginning or find the next available slot to store, because then I can't find it at random, right? So there's no next pointer or anything to point me. So I have to follow this strategy to store Greg so that I can find Greg, right? So that's open addressing. Again, to find Greg, I'll do the same thing. I would send Greg through my hash function, and then I would find the index by modding it with my hash table size. And I see that in slot 3, where Greg should be, is David, which means I had collision. So I'll go to the next slot and compare. And I found Greg on the next one. Okay. Questions on collision and collision resolution, called open addressing. So far, so good. Okay, Thomas is good. What about the rest of you guys? Okay, very nice. All right. So open addressing is easy to implement. But as I said, the problem is that if you do run out of all slots, you're going to have to, if you run into repeated collision, you're going to have to find a new slot, a new location for this whole data set, right? Which is a common problem with arrays. So we want to avoid that. So we want to find a better collision resolution, which is called separate chaining, right? And most hash maps are implemented using separate chaining because it's a better way to do this. You never have to relocate or anything like that, right? So separate chaining uses the hash table, which is the array. But when you run into collision, instead of, so notice this one is using the array and finding the next available slot. Separate chaining says, well, I have a collision. So where I have a collision, I'm basically going to build a linked list right there, right? So my hash table is an array, but every single collision is resolved by using a linked list. So 3 is my index where David should be, right? So I would take 3 and make that my head and store David there. So next time Greg comes in, Greg wants to go to 3. And so I'll start at the head and I would say, okay, the head's next pointer points to David. And then David's next pointer points to nothing. So I'm going to put Greg there. So I can actually build up this linked list, at each one of these index. In fact, you can actually you can use a doubly linked list here. You can use a binary search tree. You can create any data structure here. But the idea of separate chaining is that instead of finding the next available slot in my hash table, right, I'm going to use another better data structure in that index. So that way, I don't have to. That eliminates the copying and relocating to another place. Okay? So this is an array, and this is a linked list going up. All right? So separate chaining, the common way of implementing separate chaining is a linked list. Okay, so performance on a hash map. Hash map performs O1 unless you have collision. Collision slows down things in hash map. That's why we want a good hash function so that it does equal distribution. We also don't want our hash table to be very small either, because the smaller the hash map is, the more chance we have of collision. The fuller the hash map is, we have a higher chance of collision, right? So collision slows things down. Doesn't matter whether you're using a linked list or an array. That O of 1 insertion becomes O of n. Because I go to 3 and David is there. I have to go find the next slot. Let's say the next slot is taken. I have to go to the next. That's taken. So that makes it O of n. And if you're using a linked list, again, it's O of n. You want to go and insert at 3, right? Well, 3 is taken. So now create a linked list at 3. Right? And then find the slot by iterating through each one of the keys. So that makes it O of n. So we want, and of course, there's no way of eliminating collision, right? We can't do that. But just know that, collision slows things down. Now, other things we can do to actually consider to make the performance better. So, for example, if you are especially with open addressing, right, you can always keep track of your hash map and say, let's check and see how full the hash map is, right? And suppose it's X% full. Let's say it's 70% full or 60% full, right? That means that you can actually go move to a larger array. So just like we did before, right? We did sensible resizing. Here, we're actually proactively moving to a larger array if we keep track of our hash map and see how full it is. Now, that will work with open addressing. For separate chaining, there's no way around it, right? But at least separate chaining eliminates the expensive copy operation. All right, to remove values, right? How do we remove values? So notice that although this is underlying this is arrays, but we're not using this as an array, right? So we can actually have gaps in memories because we're not finding items using index, we're finding items using keys, right? So if I want to remove something, you just find the key. So for example, you'd have a hash map implemented either using open addressing or separate chaining. So if you're using separate chaining, find the key in the linked list, remove the item from the linked list, standard remove operation, moving the pointers, right? Just like you did removing a linked list. For open addressing, you just find the key, right? So suppose I want to remove JS from here. So find the key that resides in 0, right? So I found it. All I have to do is flag it, right? So I basically indicate that location. It's still part of the array, but I'm going to indicate, I'm just basically going to put a flag there saying this is an empty slot so someone else can use it. And that's it. And next time, let's say another key value pair gets mapped to index 0, right? It's going to see that flag and says, oh, this is actually empty. The data can be there. That's fine. Now you're just going to override the data with the new data. Okay. You don't need to, unlike the splice operation in an array, you don't need to copy or resize or remove or rearrange because we're not using this as an array. We're using it as an associative array, which is key value pair, which is called hash map. Okay. All right. Questions, guys, so far? Let's see, what do we have today? Okay. All right, here are a couple of the things that you guys are doing today. So let's see. Okay. Any questions? Last night's reading, hopefully I think that the most tough thing was going through this hash string function, I believe. But hopefully that makes sense now. Again, as I said, this is based on other algorithms. So, if you had time to read it, that's great. There are many, many other ways of creating the hash function. This is just one way we picked. But at the end, the result is pretty much the same. So for today, again, you're going to take your hash map class. Hopefully, you'll be able to write it from scratch and then create your hash map. Insert these data in the hash map and then retrieve the value for this key. Okay, and then you have a couple of interview questions. I think most of your time will be spent on this. So if you look at your hash map here, you'll find out that it's actually using open addressing. Okay, now I want you guys to actually look and see what part of this code is giving you open addressing, right? Which part of this code in this class is handling the collision by open addressing? And then that part of the code will need to change to implement separate chaining. And then you can test it by basically the same. The result would be the same. It's just you're using separate chaining, so you don't have to relocate. Okay. Questions, guys? Is this all making sense? Hopefully. Yes, no? All right. Hash.map size ratio. From here? Right here? Okay. So notice that here, when we said that if you are using open addressing, okay, who's this? Siha. Okay, so let me explain what the map size ratio is. So notice that I said, if you have open addressing, right? If you have open addressing, which means you found a slot, it collided, you have to go to the next slot and the next one, right? So in this case, you don't have a linked list, right? So you can't really go any other way, but basically use all the slots that's in your hash table. So if the hash map, if your hash table gets fuller, right? So let's say this slot is taken, this is taken, this is taken, this is taken, this is taken. So notice my empty slots are getting smaller, which means my hash table is getting fuller, which means I'm going to run into even more collision. Right? The fuller the hash map is, the more collision you're going to get. So what I can do is I can proactively, right, say, okay, if this hash map is, let's say, 70% full, right, which means 7 out of the 10 slots are taken, I am going to proactively go to a larger size. And that larger size is the size ratio. So whatever the length is now, I'm going to go 3 times bigger that length. So if I have 10 slots now, I'm going to allocate a hash map which is 3 times larger than my current one. So the new location, I'm going to have a hash table of size 30, right? And the max load ratio in this case is 90%, which is a little too high, but that's telling me this percentage, right? I'm keeping a track of how full the hash map is. If I have one item in there, then it's only, it's only 10% fuller. So I'm going to keep track of this. And when it gets to 90%, right, that's when I'm going to say, okay, I'm not going to wait till I get completely full and I try to insert something and I get an error. When I'm 90% full, I'm going to go to a newer location. So that's what these two ratios are telling you.
Okay, thank you. I understood.
Okay.
I'm okay with the 90% of loading ratio is okay, but I just wonder the size ratio, how we decided. Okay, I got it. Thank you.
Yeah. So here we're just telling that take the current size and then make it 3 times bigger. Okay, the other question Kevin had, what does a naive solution refer to? What do you mean? What is it? What are you referring to? The naive solution. So if you go back to your array days, go back and look at your slides from your arrays. We had naive solution and sensible solution to resizing an array, right? So a naive solution to resizing an array would be, okay, I have 3 slots in my array, right? They're taken and I want to push another item, right? Let's say I want to push a 12. So I don't have slots here. I'll find a new memory location with only 4 slots, right? 3 for the existing data and 1 for the new data. So then next time I push, I'm going to relocate to somewhere else. Next time I push, I'm going to so that's a naive solution, means that's you're basically allocating exactly what you need, right? The sensible solution in terms of an array, again, if you go back to your array slides, you'll see both of these terms. The sensible one would be, well, I am out of space. I have to insert another one, but maybe I'll push more. So proactively, I will allocate more slots, right? So that's a sensible solution in the sense that you're making sure you don't have to relocate and copy the data every time you try to push. That's what those means. Okay. Right. Any other questions, guys? Okay. Just a quick note on palindrome. So you guys have used palindrome using string, right? Reading a string forward and backward. You've used palindrome using a stack last week. Well, this time you're going to use, actually, it's a little bit different than that. You're going to find a permutation of a palindrome using a hash map. So again, if you're not using hash map here, you're doing something wrong. So you've got to use a hash map in order to find if a permutation of a string, any permutation of a string, is a palindrome. Okay. All right, guys, that's all I have for you today. Let me know if you have any questions. Otherwise, I'll see you guys at 1:30.